Hello. Today's lecture is the last lecture about linear algebra. I heard someone say yes, but it's a beautiful part of mathematics. We're going to use it. We're going to use it for the next 2 weeks in order to study differential equations and systems of differential equations. But this will be the last lecture with new things, this and on Friday. And it is beautiful. It's about symmetric matrices, and they have some special properties. So let's start. So the lecture is about symmetric matrices. I'm going to start about repeating the dot product or introducing the dot product. And I will do so by giving an intro in G2 and G3. And this is the set of plane vectors, and this is a set of vectors in 3 space. These 2 sets. And then I will continue with a generalization to the n-dimensional space Rn. And then I will talk about the gram Smith algorithm and basically if you have a set of linear independent vectors, you can create a set of orthogonal vectors. And then I will introduce an orthogonal matrix. And then finally, I will use all this on symmetric matrices. And I will list 4 nice properties. And I will give some examples. So this is the agenda. We have heard about the dot product before, but let's repeat from the set of plane vectors and vectors in space. So, given 2 vectors, A and B, and you have an angle between the 2 vectors, then we defined the dot product A times, or dotted with B, A dot B, as the length of the A vector here times the length of the B vector times cosine to the angle between the 2 vectors. And this immediately means that if these 2 vectors are perpendicular, that is, If they are perpendicular, the angle between the two vectors is pi half, or 90 degrees. So, and cosine of pi half is 0, so the dot product is 0. And this is A perpendicular to B, or as we say, A and B are orthogonal. Also, we have previously introduced in G2 and G3, G3 the standard basis. And I do so here in G3. We have the standard basis, and this standard basis is orthonormal. And I'll tell you what that means. It means that the length of the standard vectors are all equal to 1. That is, they are normal. This, or they are normed. They have the length 1, all of them, and they are mutually perpendicular or orthogonal. So, if I have the I vector here and the J vector here, this angle is 90 degrees. And here you have the K vector, and these angles are all pi half or 90 degrees. And this means that I times J is equal to 0, I times K is equal to 0, and J times K is equal to 0. Nothing much new about that. Now, if you consider the coordinates in the standard base, then you can write the scalar product or the dot product in coordinates. Let me show you that. I have A, and now I have coordinates, say A1, A2 for the A vector, and I dot this with the coordinates for the B vector, that is B1, B2, and this is equal to A1, B1 plus A2, B2, and if it was in space, then you have a third coordinate, and you will just have one term more here. Remember that the length of the vector A is equal to A1 squared plus A2 squared. Using the dot product here, we can write this as the square root of A vector dotted with the A vector. That is, if you put B equal to A, you get A1, A2 here, and you get A1 squared, A2 squared, and taking the square root of that, you end up with the length of the vector. Now, enough of the introduction. Now I will do the generalization. to Rn. Now, I have A times B, and in terms of coordinates in Rn, standard basis, you have A1, A2, An. And this you dot with B1, B2, Bn. And it's equal to A1, B1 plus A2, B2 plus An, Bn. So this is the dot product in Rn. And now it becomes easy to define the length of this vector here, because this will simply be the square root of A dot A. So this is the generalization of this formula here. And now you can also discuss, although if n is greater than 3, you cannot imagine how that will be, but you can define the angle between two vectors. Between A and B. And this is determined by cosine of V and then divided by the length of A and the length of B. So let me compute an example. So I take as the example, I have the vector 1, 1, 1, 1, and then the vector 1, 0, 1, 0. And I will compute the length of this vector. So this will be the square root of, say, the A dot B. And A dot B, you have to multiply the coordinates 1 plus 0 plus 1 plus 0. That is the square root of 2. No? This is wrong. It's, of course, if it is the length of A, then it will be the square root of A dot A. And this will be 1 plus 1 plus 1 plus 1. I just write it. And this is the square root of 4, and this is equal to 2. And similarly, we have and this will be then 1 squared plus 0 squared plus 1 squared plus 0 squared. And this is 2, so this is square root of 2. Now, let's try to compute the angle between these two vectors. And I use the formula here that I take the dot product, that is A times B, and then divided by the length of A and the length of B. And this dot product here is 1 plus 0 plus 1 plus 0. So this is 2. And then divided by 2, length of A, and the length of B is square root of 2. So this is the square root of 2/2, or 1 divided by the square root of 2, which is the same thing. And then, of course, you know what the angle is. Yeah. Pi over 4, yeah. Okay. Now, the standard basis or I should say bases are orthonormal. And I give you an example from R4. You have that the standard bases are these. And then finally, E4 is 0, 0, 0, 1. And say if I take E1 dotted with E2, I get 1, 0, 0, 0. And then I dot it with E2, which is 0, 1, 0, 0. And you see that this is 0 plus 0 plus 0 plus 0, so this is 0. They are orthogonal. And you can see here that the lengths are all 1. So, and this goes, of course, also for Rn, where n is arbitrary. Now, you will shortly need to be able to take a set of linearly independent vectors, and from this you should form an orthogonal set of vectors. In fact, an orthonormal set of vectors. And there is an algorithm for doing that. And I'm going to go through this algorithm now, and you will have plenty of practice with this algorithm this afternoon. And you will, though, only do it by hand this afternoon. After that, you will use Mabel to do it. But in order to understand it, I'll go through it. But first of all, I would like to repeat, and this is kind of an intro to the Gram-Smith algorithm. And what I'm going to repeat is what is the projection of a vector on a unit vector. We have had that before, but let's take a vector A here, and we want to project this onto a unit vector. And here I just draw an auxiliary line here. And then I draw the perpendicular on this line, like this. And we have an angle between the two vectors, V. And now the projection of A on this vector here is this vector. And we call it the projection of A on E. So it has two arguments, the vector itself and then the unit vector that you project the vector on. Now, first of all, I will compute the length of this vector. And here you have two vectors, and you have the angle between them. So if you use your old school arithmetic or trigonometry, then this will be the length of this side here in this right-angled triangle. So it will be A times cosine of V. So this is equal to A times cosine of V. Now, this is a unit vector, so it has the length 1. So I can introduce this simply like this. I won't change the equation by this. Now this here is simply, this is simply the scalar product of the two vectors A and E. Remember, well, we defined it right up here, and it generalizes, of course, to Rn, and we get that this is A dotted with E. So this is the length of the projection. Now the vector itself, as you can see from this drawing here, is that the resultant vector here, the projection, is collinear with E, with the unit vector here, parallel. If the angle is larger than pi half, it will point in the opposite direction of this unit vector. But if the angle is less than pi half, then it will point in the same direction. But in either case, you have that the projection of A on E is equal to the scalar product, and then times the vector E. Okay, so now I have the tool that is needed in order to introduce the Gram-Smith. So we are in Rn, and here we have a subspace we call it U. This is a capital U, and It has the basis U1, U2, and UP. And we assume that all of these are linearly independent. All these vectors here are linearly independent. And that is, these vectors span a p-dimensional subspace in U. And the question is now, can we find an orthonormal basis for the subspace U? That's the question. Now, let me draw the situation in 2 dimensions. You can always choose 2 vectors and look at this subspace spanned by these 2 vectors, and then you will be able to draw it. You have the vector U1 here, and then you have another vector U2 here. Now, the first vector is very easy to find, because you just choose U1 as the first vector in your system. It may be not normed, but you can do that easily. So what you do is that you divide by the length of the vector U1 to create your first vector. And I write this as is the vector U1 divided by the length. So this has clearly unit length, and it is in the direction of U1. Now you want to use the information in order to create a vector that is perpendicular to U1. So let me draw a line here that is perpendicular to U1, and it goes through the end of U2. So if you look at this triangle here with this right angle, then if you have this vector here, I call it W2, and the reason is that it doesn't have unit length, so I have to divide by the length later on in order to get a unit vector in that direction. But in that direction, it is perpendicular to V1, that it is orthogonal to V1, and I can compute this vector. What I do is that I say U2 is the sum of this vector here and this vector here. And this vector here is the projection of U2 on the unit vector V1. And we have just seen what this vector is, but I take this auxiliary vector V2, and from this triangle here I can see that it is the vector U2 and minus this vector here, which is the projection of U2 on V1. And then I just use this formula up here, and I get that it's equal to U2 minus, and then I have the dot product of the two vectors, U2 and then times the unit vector V1. So this is this vector here, and in order to get an orthonormal basis, I norm this vector. That is, I divide it by the length of the vector. So let me just frame these two. So now I have two vectors, but it's p-dimensional, and you have to create p-vectors. So, and I will just introduce that by creating the third vector. And I hope I can make a nice drawing of that. I think I'll do it up here. Yep. So let me draw the two vectors I have found. That is, I take here V1, and here I take V2. These are unit vectors. And then I take the third vector. It is linearly independent of these two vectors, so it cannot be in the same plane as these two vectors. So let's see if I can draw this. This is a bit long. So they are unit vectors. This is. So I just draw here a box, an auxiliary box, in order to see if this will. So what I'm looking at is this vector here. From the origin here and then to this corner of the box. Now I do this. I say, and I should write here. This is the vector U3. So from this drawing here, I can construct a vector that is orthogonal to these two vectors and which has unit length. So what I do first is that I draw some auxiliary vectors. This is A, and this is W3. And I do that because I can say that U3 is A plus W3. And since W3 is perpendicular due to the construction, this is just the projection of U3. A is the projection onto the V1, V2 plane. So this is perpendicular to these two vectors. Then I have the third vector in my orthogonal basis, and then I can norm it, and it will be my orthonormal basis. Now I do something further. Maybe I should do that in red. And that is the A vector here I can compose by these two vectors. That is the sum of this vector here and this vector here. Maybe I should call these, if I call these for x2 and x1, then I can write this as x1 plus x2 and then plus W3. But what is the x1 vector? The x1 vector is the projection of U3 on the unit vector V1. If you draw this, and now it's becoming a bit crowded. If you draw this line from this corner here up to this corner here, which is the diagonal in this side of my cube, then you can see that you have a right angle here. And so the projection of this down here will be x1. And similarly, the projection onto V2 will be x2. So this is simply the projection of my vector U3 on V1, and then this will be the projection of U3 on V2, and then plus my vector V3. Now, I can solve this with respect to V3, which is the vector I'm looking for. So that will be U3 and then minus this vector here. And this vector here is U3 times, or dotted with V1 and times V1, and minus this vector here, which is then U3 dotted with V2 times V2, and then you have that V3, the V3 vector, you simply norm this. That is, you take the vector and you divide it by the length of the vector. So let me frame this as well. So now you have the three first unit vectors or orthonormal vectors in your setting. And you continue this process. this, the vectors you have to subtract from the new vector, it becomes more and more vectors you have to subtract. And if I look at the final vector, remember we had p linearly independent vectors, then you get up times b1, and then minus up times. And then finally you have up times vp minus 1, vp minus 1. And then what you do finally is that you norm this vector. That is, you take this vector here. Okay, I'll take a break for 10 minutes now, and then I'll continue with an example of this.